Okay, so here are three examples of molecules and if they're polar or not. Okay, so here we have CH, maybe I'll make this, move this. Can I move this down? Okay, so let's look at this. I want to look at this nice and big. We'll make them each big. So we have CH2O. So first of all, here's the Lewis structure. So let's take a look at the criteria. So the carbon does not have lone pairs of electrons. So that first part, this first one does not apply. The carbon has no lone pairs, and there are two different types of elements, oxygen and hydrogen. So what that means is we'd have to check the difference in electronegativity between CH and CO. So when we do that, the CH bond is nonpolar. It's 0.35, which is covalent bond, but the carbon and oxygen is a polar covalent bond. So notice the dipole is drawn in. So that's what this star is. The dipole is only drawn when there is an uneven distribution. So when you have a polar molecule. So let's recap why this is polar. There's no lone pairs on the carbon, and the element does not have the same types bonded to it. We have oxygen and hydrogen, and one of those bonds is making a polar covalent bond. So that makes this whole thing, the molecule is a polar molecule. Now, if we were to look to the types of bonds, this molecule has two types of bonds. It has a polar covalent bond here and a non-polar covalent bond. So if you're asked to discuss the types of bonds, this has two types, a polar bond and a non-polar bond. But the molecule itself is looking at the entire picture, not just one bond over another. Okay, so let's look at this next one. So carbon has carbon tetrafluoride. So there's only 4 fluorines here. So with carbon, there are no lone pairs around the carbon. So the first rule doesn't apply. And if you look at the elements, they are all the same. So this is a non-polar molecule because the carbon and fluorine has carbon and fluorine on every spot of that molecule. And actually, if you were to discuss the bonds, carbon and fluorine, if you look at the difference in electronegativity, this is a polar covalent bond. So the bond itself is polar, but because it's the exact same bond in the entire molecule, it's what we call symmetrical. Wow, I can't spell. So it's what we call symmetrical. 2 M's. So meaning this molecule is evenly distributed. The bond is polar, but as a whole picture, it is non-polar overall. So that's why it's important to distinguish. Are you talking about the bond or are you talking about the molecule? That's why I have them as 2 separate lessons. The bond is just looking at the electronegativity, but the molecule, you have to look at the big picture overall. All right, let's look at the last example here. So for the last example, we have boron trichloride. So boron has no lone pairs on the central atom. Okay, we have 3 elements bonded and they are all the same. So this is another example of a non-polar molecule because they are equally distributed in this structure. So we have chlorine, chlorine, chlorine. They are all the same. So it's only when they are different. So let's say we had hydrogen, chlorine, fluorine. That means you have to check the electronegativity. As long as if you have one polar bond, the whole thing is determined to be polar. But in this case, they're all the same. Okay? So for this next part, there are 3 examples here, so 3 more compounds. What I'd like you to do is draw the Lewis structure for each one and then indicate if it is polar or not polar. So pause the video, give these a try. Okay, so you should have your nitrogen has a lone pair of electrons with the 3 hydrogens. So because there's a lone pair of electrons, you have to still check to see where is the polar covalent bond. So the NH bond is a polar covalent bond, and you should have your dipole pointing towards nitrogen because nitrogen has the higher electronegativity. Or if you prefer and you want to draw the delta symbols, your nitrogen should have the delta negative and your hydrogen should have the delta positive. So remember, you don't have to show all 3 of them. As long as if you show 1 for each new type of bond, that's sufficient. Okay, so overall, this is polar because of the lone pair and the polar covalent bond. Okay, for the next one, you should have sulfur with 4 oxygens, and actually all the oxygens have their full octet. Because this is an ion, you should have brackets with the charge in the corner. And this is actually non-polar because sulfur has no lone pairs, and every element bonded to sulfur is exactly the same. They're all oxygens. Carbon dioxide is also nonpolar. So carbon has double bond with each oxygen. And double bonds actually are not looked at any differently than single bonds here. What we're looking at is the types of elements. So carbon has no lone pairs of electrons, and it's the same element that's on either side. So oxygen and oxygen. So this is a symmetrical, even distribution. So that is non-polar. Okay, so molecular compounds come in a variety of different properties. So we already looked at ionic compound properties before. So molecular compounds come in a variety of states. So some are liquid, some are solids, and some are gases. But usually the ones that are solid are not overly hard. Okay, remember SATP stands for standard ambient temperature and pressure, which is basically room temperature. So a liquid at room temperature, a gas at room temperature, or a soft solid at room temperature. So normally they are non-electrolytes, so meaning they do not conduct electricity. So they're the opposite. So in terms of conductivity, it's the opposite of ionic compounds. Compared to ionic compounds, their boiling points and melting points are relatively low. And the reason for that is this next point here. The reason why they have low melting points and boiling points is because their intramolecular forces are strong, but they have weak intermolecular forces. So you don't know these terms yet, but you will, okay? Let's talk about it briefly. We're going to spend the whole next lesson after this is looking at these forces. So intramolecular forces is actually something you've already learned about. Intramolecular forces is another way of saying bonds. So when the question is saying, what is the intramolecular forces for the following molecule, they're talking about what types of bonds does that molecule have. So really there's 3 options: covalent, polar covalent, or ionic, which is what we've been spending time doing over the last few lessons, right? Starting in chapter 2. Intermolecular forces is what is new for us right now. So intramolecular forces is not new. We've just finished learning them. It's just that this term hasn't been used before. Intermolecular forces is a brand new concept. This is where we are talking about the forces of attraction that are between molecules and other molecules. there are 3 types of intermolecular forces, and we're going to go through these in the next lesson. So we have London dispersion forces, dipole-dipole forces, and hydrogen bond forces. What I want you to understand is the difference between intra and inter. So these little structures here are water molecules. What intramolecular forces are talking about how are these atoms bonded to each other? What is causing this atom to stay to the other atom? So in this case, it's the types of bonds, right? Intermolecular forces is looking at all the different water particles and how do those water particles interact. So think of interact when you see inter. How do molecules interact? Intra is like internal. We're looking at the bonds inside the molecule or the structure. Intermolecular forces means between molecules. What is causing the molecules to be attracted to other molecules? So these are the 3 of them here. So again, this is just another picture. So intra is talking about the bonds. Inter is talking about the attraction between different molecules, like molecule to molecule. Okay, so we'll look into that more in the next lesson.